One of the most important things in computer vision is our training data and also just in AI in general. In this video here, we're going to go through some techniques that you can use to auto label and annotate your datasets before you go in and either fine tune or pre-trained object detection models. So this can both be used for intersegmentation, object detection, where we have the bounding boxes around it. Take a look at some techniques that can significantly increase the speed of doing annotations. It's a pretty trivial task. It takes a long time to go in and annotate images. If you're using annotation services and all that, they're very expensive services too. But trash into the models is also trash out, so focusing on the dataset is very important. Inside Voxel 58 here, they have a developer tab. You can read more about it. It's basically just an annotation and labeling platform. Supports all the different features that you need for setting up the whole pipeline. And they have just released a research paper that we're going to read more in details about. I'm going to explain some of the technical details, but also practical results. So the most important thing here is that this is practical research, how we would use these models out in the real world, and not really too much technical details or trying to do something too hardcore. So right now, if you go inside 51's documentation, you can read about how you can install it, set up the environments. It's basically just pip install 51. You will get this interface where we can go in and do our labeling. So you probably know all the other tools and so on, but here we have everything combined. So we have the model zoo, dataset zoo. You can see how we can do integrations with Coco, OpenCV, all different types of integrations they have out of the box. So you can label your dataset in here, train a YOLO model directly out of the box like this. So we can load the dataset, train the model directly as we used to with Ultralytics. So it's just a few lines of code. But right now, let's go in, dive into the research paper and get more practical where we can see how this actually works. So first of all here, the main idea behind doing auto annotations and auto labeling is to save time. So it's a very trivial task, takes hours, if not weeks and months, depending on the scale that you're annotating your dataset on. But now we're going to use some of the foundation models. We have the vision transformers, where you probably know all the different visual language models and so on. There are some models out there that we can use. Maybe the YOLO-World, you've heard about that. That's one of the models that they test out throughout this research. So it's a practical research, just comparing all different techniques and foundation models, which are the best ones and what results do we actually get when we use auto annotations versus a human labeler. So let's just go all the way down here to the first graph and take a look at the figure. Everything will be down in the description, so you can grab the research paper. You can check out Voxel 51 if you're looking for data annotations. But here we can see the main trade-off and benefit is basically just we want to compare human labeler and auto labeler from a foundation model. We don't really need like a crazy huge foundation model. You've probably heard about Grounding DINO, SAM models. We have the YOLO-World model as well, where we can basically just prompt it to go in and detect what we want to annotate in our image. So first of all, when we tackle a computer vision problem, we start with unlabeled data. Then we can start doing auto annotations, or we can use standard labeling as a human. So just drawing a bounding box can actually take up to 7 seconds, depending on like how good accuracy that you want as well. But if we want to have good bounding boxes, it at least takes a few seconds, depending on the class, and all the way up to 7 seconds. So if you have like tens, hundreds of bounding boxes that you want to label in your image, and you need thousands of images to be able to train a good model that can get into production, that's going to take a crazy amount of time compared to some of the auto annotation tools. And the trade-off is actually pretty low compared to the amount of time and cost that you're saving. So we get our auto labelings. This is the bounding boxes. We have our standard labeling. Then we can go in and do similarity comparison on a label as well. So we check how different are the labels. If we just zoom in a bit more here, then we're basically just going to overlay the two labels on top of each other. We can calculate the intersection over union and so on. So how much do our bounding boxes actually overlap? Then we can go in and compare the model validation accuracies. So this is pretty much just a pipeline that they're setting up, testing out different models inside this paper. Very practical guide, as I mentioned a few times. Then we can train a model on auto labels and train one on human label, and basically just compare the model validation accuracy. A little teaser now, we're going to see some very interesting results, and it's actually worth it to go and use auto annotation tools compared to spending time on it. You can always go in and refine it after. Again, you can have your auto labels, then you can go in and refine it with a human reviewer as well. If we go a bit further down and start take a look at some of the datasets that they're using. So we have Object 365. They're going to use a VOC, the COCO datasets, all these different base model datasets. So we have a huge dataset. We have a model, random initialized weight, then we train and pre-train our model on those datasets. So it's tens of thousands, hundreds of thousands of images, and then after that we can just with a few thousand images go in and fine-tune those models. We can also train from scratch, which is actually pretty nice, and we get very good results with that from this paper if we actually have good enough labels and of course enough data. So trash in is trash out. Remember this here, it's not really the models. If you're using YOLO, RTD-ETR, RFD-ETR, whatever model that you're using out there, if you don't have good data, you will not get good results. So first of all here, a very cool one here is just inference models used for auto label based training. So YOLO models, RTD-ETR, this is just inference time, the baseline VOC validation performance before we actually go in and compare it with the human labelers. So this is the baseline performance that's going to be compared with for the COCO dataset. So this is the foundation models that are used for auto labeling, YOLO-World, YOLO-E, and Grounding DINO. So these are some different variations. There's also other models available out there, but these are still relatively small. That means that it can label your data very fast still, and like in seconds instead of like taking 10-20 seconds if you're running like larger SAM models or similar ones. We get very good performance with the YOLO-V model. You can just prompt, I want to detect person, I want to detect a cat. Any object out there, you can pretty much just go in and do it. It has been trained on the Object 365 dataset, and also the other ones here, which just contains tons of classes, like thousands of classes, which is covered out there. And then of course, then you'll go in and fine tune it after, but we still need to get very good performance on our pre-training. So this is the experiment dataset, VOC, COCO, LVIS, BDD. So this is for autonomous driving. This is LVIS dataset, which has 1200 classes. We have the VOC, which is a smaller dataset or a smaller dataset with classes. And then we have the standard COCO dataset, which most models are pre-trained on. It's very important when you choose the correct dataset when you do these experiments, because again, the more classes you have, the more the model should actually be able to generalize across classes. We will be able to see some cutouts as well, where we can base it based on the confidence score. That has a huge effect. But it's very nice. You can't just go in and take one data set. It works on your data set that has a few labels, or another data set that has 80 labels for a COCO data set if it's not representing the actual use case that you're trying to solve. So this is why they have a lot of variation. They have some data sets with tons of classes, other classes which is more, or like other data sets which are more specific to a specific use case, like autonomous driving here. So this is the labeling cost that they estimate. Again, you can use like Amazon services. There's tons of different labeling services out there, and some of them, as mentioned here, is like $0.036 per bounding box, which is actually like pretty expensive with the AVS SageMaker. Could probably be cheaper, but again, if we just compare it and say we want to go in and label a base dataset that we can pre-train our model on before we do fine-tuning. Here we have 40,000 objects, 20 classes. We can also go down. So these are base data sets. You will not use this if you just want to fine tune it on your own specific application. Then it will probably be similar to the VOC data set with 40,000 objects. That's pretty much just, let's say that we have a data set with 4 classes per image and we have 10,000 images. Then that's pretty much covered. $1,500. This is the annotation service cost if you have that, but if you're using an auto annotation tool, it can pretty much be trained in like less than 10 minutes. You have to spin up the service and everything, but less than 10 minutes, and the cost is less than $1. Even if you spend an hour on it, a GPU, you can get a relatively good GPU for under $1 an hour. So this is pretty much just very important to keep in mind. This is how they set up all the comparisons, the data sets. Now we know the data sets, we know what foundation models or auto labeling models they're going to use. If we scroll a bit further down, then we can see the human label based evaluation of the auto labeling across all confidence thresholds and data set. So it's really important both for the data set, but also basically just the model that you're training on, what confidence score do we need to choose, and it actually has a very large effect on the results that we're going to get, either if you want to run inference, but also just if you want to choose a confidence score for our auto annotation tool or auto label foundation model. So number of objects, we have precision, recall, F1 score. This is very important to keep in mind because a lot of people think that we can just have a high confidence score for auto annotation tool. We could have that if you want to have a human reviewer. We just want to have the initial bounding boxes with high precision from an auto labeler. Then a human labeler can go in and annotate the rest, where the foundation model or the auto labeling model has lower confidence. This could be one of the reasons or use cases where you might want to have a higher confidence score. But if you just want to have like a cutoff trade-off between precision and recall, these are some pretty good graphs depending on the data set that you want to do it on. You can also do it on your own data sets. It also depends on the models. So this is why it's good to have these comparisons. So number of object labels. Here we have the number of images or labels. We have the confidence score. So for example, we have the gray dashed lines that the human reviewer. So if you're using the grounding DINO with this data set, then we need a confidence score around here if we want to have it a good trade-off with a human labor as well, which is like an optimal threshold. These are very important because you can see how large effect it actually has. For example, if the BDD, this is representative of a data set that is used for real world applications. The other ones is more benchmark data sets, but this one here, you can see depending on the model that you're using, you need a very different confidence score. The F1 score here is relatively low for this specific data set because again, it's still specific, and the auto labeling model here has not specifically been trained on this data set, but more these benchmark data sets as the VOC, COCO, and all that. So the highest F1 score is basically this one up here on the VOC data set, where we only have 20 classes, so that also makes sense. But we want to have a trade-off between precision and recall, and this is where we can see it with the F1 score, and then we can basically just go in and take a look at the cutoff. So here, a confidence score of 0.5 is pretty good for the VOC dataset. If you want to have a trade-off between them, we can see what we need to set it to if we want to have higher precision as well. So this is what you can use these tools here for, or at least these graphs that they have done. So they're doing practical comparisons on different data sets. I really like that they're both using benchmark data sets, but also some more like real world use cases, but also covering different amount of classes. So this is very important to keep in mind. It's very good paper. Definitely check it out in more details because it covers everything that you need for practical use cases when we focus on the data part of it in a computer vision pipeline. You need to figure out the data set. You can't just go in and random use the data set. You need to actually think about what does this represent? How many classes do I have? What is the confidence score? What base model should I use? You might need to use multiple base models. Then for each base model, how do you choose a confidence score and all that? If you don't know these details that they go through in the paper for this practical evaluation, then it's really hard to get the most optimal performance. And you need this if you want to save a lot of time, cost, but also improve the results that you'll get out from the models. So here we see an example, which is a comparison of all the auto label trained inference models on the VOC validation. And we have the confidence score. So this is all the variations for YOLO and also RTDTR. So we have the human labels, we have YOLO-V, we have YOLO-E, and grounding DINO. All of them are not really getting close, or not close, but they're not getting as perfect as the human labels, but we're going to see a trick in just a second, so definitely stay tuned for that. But we can see what confidence score we need. For example, if we set a confidence score here of 0.1 and we're using the grounding DINO model, then we can see that the mean error precision actually drops significantly. So we really need to take this confidence score into account, and also why they covered in so many, pretty much just in so many charts as we can see in here. This is on the COCO validation. The YOLO-E, YOLO-V probably have similar like backbones and so on in the models, so they look very similar for the confidence score, but we can see how huge difference it has. Here's the validation performance on the COCO dataset. I want to scroll a bit further down and actually take a look at where we go in and compare it together with a human. So now we pretty much just covered all the important parts here. They also have a label evaluation metric versus the also labeled train inference model validation, where we can see what does actually like give the best performance and the number of labels that is correct. So train label, F1 score, we have the number of classes, we have the precision recall. Again, recall is how many detections are we missing, precision is how many accurate predictions do we actually get. So false predictions is recall, or mispredictions is recall, and pretty much our precision is how many correct predictions are we getting. So sometimes it might be useful to have higher precision if you really want to be sure that your model is performing good, and you might be able to accept that you missed some detections, but it could also be other applications where we don't really have room for losing detections. We can also always apply other algorithms and so on top of our detections or the results that we're getting. We just want to make sure that we're not missing any detections at all. Then we need to make sure that we're looking at the high recall values. Here for the confidence score, we can see the black values. They're generally way better when we have a confidence score of 0.2, 0.5. The alpha score here that they're mentioning is just the confidence. So generally, we get way better performance when we have the lower confidence scores for both precision recall and the trade-off. So let's go down to the fun part here and actually see how much does it drop in performance. Is it better? Is it performing better? What is the trade-off of using these auto labeling tools versus a human labeler? And if we just take a look at it, here we can go through it like step by step with the grounding DINO, YOLO-E, YOLO-V. This is probably the most interesting chart to look at and the most practical one if you just want to use it out of the box and don't want to spend too much time on doing the labeling, validation, testing out different models and so on. It's very important, but if you just want to get a quick overview over what does the research paper here actually conclude, we can see it right here. So this is the inference model class, error precision 50 on the VOC validation. There's also on the COCO validation set. So this is a bit more representative if you want to like fine tune a model on 20 classes for our own data set. So let's take a look at it. We have the classes. This is the 4 most common classes, and this is the 4 least common classes, or 5. So 5 most common, 5 least common. This is also very good practical use case because again, we don't have too many examples of these ones here. So how does our model perform on those exact examples? For example, if you use a pre-trained model out of the box, you get very good accuracy on the person, car, chairs, and all that. It's very common object. It's a large object, and we have tons of data that it has been trained on. Let's take a look at just the confidence score, like 0.2 for all of them, or let's take a look at the highlighted value. So human label, here we drop around 1% in performance, maybe 1.5% in performance by using an alternate annotation tool with YOLO-V. If you're a quick thinker, if you look at this chart here, you can easily see that maybe the YOLO-V model, the YOLO-V model is the best model for actually using auto labeling. So you might just go with that if you look at this chart here. And then the next tip that I'm going to show you is basically when we take a look at it and take a look at the different variations for the different YOLO models. I'm going to show you something in just a second. So human labeler, we drop a bit in performance. Here again, we drop a bit in performance, around 1-2% we drop performance, at least on these common classes. If we go down here and take a look at it, here we actually get better performance for trains because again, there could be many reasons for that. Here we drop a bit in performance, or we actually drop 5% in performance. Here we get better performance as well. So it really depends on how many examples are actually in the data set. This makes sense. Here we get better models, but on the more general classes, we get lower, or at least a bit lower compared to a human labeler. But you can have this hybrid approach as well, as I mentioned. Let's go down and take a look at the last graph here. So now we've gone through everything. Now we're getting to the best part here. We covered the whole pipeline pretty much step by step, but what is the conclusion? Here we can save a ton of time when we do our auto annotations. We saw that we lose a bit of performance, but maybe we can do something about that if we take a look at different model variations, or where we can basically just focus our resources more on. Could be that we can spend the money, the resources on getting more compute power, doing more model optimization and so on, instead of spending time on the labeling part. Just from this table here, and also if you do more tests, let's say that we're running with a YOLO Nano model. We use the auto annotation tool. We can see that we drop almost 0.04 in value. So this is actually like a significantly drop compared to if we used human annotations. But what if we actually just bump up our model size once? So instead of going with the nano model, we go with this small model. This is going to increase the inference speed a bit, but we also get higher accuracy, as you can see here. So yeah, if you use human labeling and you act like just bumped it up one model, it will take significantly longer. Like it'll take days to weeks to label your data set, and then you act like get slightly better performance. But we can just jump up one variation in the YOLO model, and the best one, take a look at this one and this one. It's side by side. We get better performance if we just use a larger model with our auto labeled images. This is pretty much the conclusion. We went through everything step by step, all the way down to how do we actually set up a comparison? How do we do a practical comparison and evaluation of how these data sets work, and also the direction? Because these foundation models, they're only going to be better when we need to use auto labeling tools when we label our data set. Just takes too much time, resources. It's very boring work to go in and do. We can always have the hybrid approach where we have very high precision, and then we have a human labeler that verifies it and also corrects the labels. This can save some time. This is some very cool findings from this paper. Go through it in details if you're a computer vision engineer, like working with model developments, focusing on the data set and all that, because at the end of the day, trash in is trash out. We want to be as fast as possible, iterate fast, don't spend time on the boring part. We want to optimize our models, optimize our data set, build use cases and applications around it. Hope you learned a ton this video here. Like, this is a full walkthrough. We're going to use the tool where we're going to show how we can use these auto annotation tools. Stay tuned for that, and then train and actually computer vision models. Then we can do the comparisons ourselves and see how good does it actually perform. Go through the video again. Like, I really recommend that because there's so many details covered. The paper is really detailed as well, but this is how you can do evaluation of models. And also keep in mind, most people, they forget to keep these things in mind. How do I evaluate something that represents the data, represents the real world that I'm actually trying to solve? Hope to see you guys in one of the upcoming videos. Until then, happy learning.